Moving on to the next topic in hydrogen chapter, water. A major part of all living organisms is made up of water. Human body has about 65% and some plants have 95% of water, and water is crucial for the survival of all life forms. Now next we have physical properties of water. Like we know, water is colorless, it is tasteless and has a high boiling point. So we have chemical properties of water next. First chemical property of water, acid base character. Water has acidic character as well as basic character in it. That means water is amphoteric in nature. The substances which shows both acidic and basic character, these are called amphoteric in nature. Like in this example, water when reacted with ammonia, water gives its H plus ions to the ammonia and ammonia thus changes to NH4 plus ammonium ion. With the loss of H plus, water changes to OH minus hydroxyl ion. So water here is losing H plus, that means this is an acid. Ammonia is gaining H plus, so this is a base. In this example, when water reacts with H2S, in this case H2S gives its H plus to the water and now water changes to H3O plus hydronium ion, and by loss of H plus, H2S changes to HS minus. Now here water is gaining H plus, so water is a base here, and H2S is losing H plus, so this is an acid here. So in this reaction water is acid, in this reaction water is a base. Since it can show both the characters, acid as well as the base character, that is, it behaves as an amphoteric substance. Second chemical property of water is oxidation, reduction, or we can say redox reactions. Water shows oxidation as well as reduction, that is, it acts as an oxidizing agent as well as reducing agent. So first is as an oxidizing agent. Water when reacts with active metals like with a sodium, with a calcium, etc. When water reacts with these active metals, we are getting in this reaction NaOH and H2. So in this reaction, from water hydrogen comes out. So hydrogen comes out from this, it is an oxidizing agent, there is liberation of hydrogen here. So this reaction shows that water is acting as an oxidizing agent here, and sodium here is a reducing agent. Similarly, when steam is passed over, when we are passing the steam over red hot coke, then we get a mixture of CO and H2 which is called a syngas or water gas. This reaction takes place in presence of nickel and on heating. In this reaction also, since from water hydrogen comes out, this shows that water here is an oxidizing agent. This takes oxygen and changes to CO. So this is acting as a reducing agent here. So these are the two examples to show that water is acting as an oxidizing agent. Apart from its oxidizing agent character, water also acts as a reducing agent. It also acts as a reducing agent. Oxidizing agent is when reacted with the active metals here, and to show its reducing agent character, we are taking an example of reaction of water with active nonmetals with highly electronegative elements like fluorine. So when water reacts with highly electronegative elements from water, oxygen comes out as O2 or O3. In this reaction, we are getting O2 plus hydrogen fluoride. There can be removal of ozone also. So in both these reactions, from the water, oxygen is coming out as O2 or O3. That means water is a reducing agent. So in these reactions, water is a reducing agent and fluorine is an oxidizing agent, because in this hydrogen is added. So this is acting as an oxidizing agent. In these reactions, water acts as reducing agent and itself it gets oxidized to either O2 or to O3. So these reactions are showing that water can act as oxidizing agent as well as reducing agent. So this is the second chemical property of water, that is, it shows redox reactions. Third chemical property of water, hydrolytic reactions. Hydrolytic reactions. Hydrolytic is from a word hydrolyze. So water can hydrolyze many oxides of metals or non-metals. Like this is phosphorus oxide, phosphorus pentaoxide, an oxide of non-metal. Or in place of oxides of metal or non-metal, there can be the nitrides also and hydrides also here. When water reacts with these, water hydrolyzes these oxides, hydrides and nitrides of metals and non-metals to form acid or base. So if in any reaction water is reacting and forming acid or base, that is called hydrolytic reaction. So when water reacts with non-metal oxides, there is formation of an acid. This acid is phosphoric acid. And when reacted with the nitride of metals, formation of a base, aluminium hydroxide is forming here. So if water reacts with a compound to form acid or base, that reaction is called hydrolytic reaction. That reaction is called hydrolytic reaction. This acid is phosphoric acid. Next we have hydrate formation. The last chemical property of water, hydrate formation. In hydrolytic, we are getting acid or base. Hydrate formation means water as it is. So many ionic compounds in crystalline form, when we are taking them in crystalline form, like we all know CuSO4, in crystalline form when we take, it has water molecules in it. And these water molecules are known as water of crystallization. So water is as it is here. So if water is as it is, that means that is called hydrate formation. Hydrate means it's hydrated salt, or simply hydrates are formed when water is as it is in a salt as water of crystallization. and number of water molecules are specific in a crystalline form. Like in the copper sulfate, 5 water molecules. In the hydrated barium chloride, there are always 2 water molecules, and hydrated ferrous sulfate always has 7 water molecules in it. So this is the fourth chemical property of water, that is hydrate formation. So there are 4 chemical properties of water. The first one is acid-base character. Water can act as acid as well as a base. Second chemical property, oxidation reduction reactions, that water can act both as oxidizing agent as well as a reducing agent. Third reaction, water reacts with the compounds to form acid or base. These reactions are called hydrolytic reactions. And if water is present as it is in the compound as water of crystallization, then that reaction is called hydrate formation. After chemical properties of water, moving on to the next topic, a very important topic in this chapter, hard and soft water. Water is also of 2 types, hard water and soft water. What is a soft water? If in the water we add soap, then there is a lather formation. Lot of lather formation is there. That water is a soft water. But if we add soap to the water, then very less lather formation is there, or there is no lather formation. That water is a hard water. Now what is there in this water which is making it hard? That is cause of hardness of water. What is the reason for this? What is there in that water? Water is hard because of presence of bicarbonates, chlorides and sulfates of calcium and magnesium, like calcium bicarbonate, magnesium bicarbonate, calcium chloride, magnesium chloride, calcium sulfate, magnesium sulfate. If these salts are there in water, that water becomes hard water. One question, hard water does not produce lather. Like we have just done, there is no lather formation in hard water, or very less lather formation is there. Hard water does not produce lather with soap. Why? We all know soap is a sodium or potassium salt of high carboxylic acid. Like this is a soap, sodium stearate example. If we add this soap to hard water has calcium and magnesium salts. Like calcium salt I am taking, this calcium ion is there in the water. This is from water. So this water, when soap is added, instead of dissolving in the water, this soap, no micelles formation is there. Instead, this soap now in water will combine with the calcium and magnesium salts to form this compound. This reacts with the soap and forms this compound. And from the soap, sodium comes out and goes into the water. In water, this goes in water. This is in the form of a scum or precipitate. So the soap is not dissolved in the water. Instead, this is in the form of precipitates. If soap will not dissolve in water, it cannot do its cleansing action, or there will not be any lather formation. And that soap will go waste because it has combined with the calcium and magnesium rather than forming a lather or doing its cleansing action. So hard water does not produce lather with soap because of formation of precipitates or we can say scum formation takes place here. Now after knowing the two type of water, soft and hard water, next we have types of hardness of water. Now hardness is also of two types. First type of hardness is temporary hardness. From the name itself it is clear. It's easy to remove this kind of hardness. It's temporary. Permanent hardness, which is difficult to remove. What is temporary hardness? If in the water there are bicarbonates, we have done hardness in water is because of bicarbonates, because of chlorides, or because of sulfates of magnesium and calcium. If there are bicarbonates of calcium and magnesium, that water is temporary hard water. But if there are chlorides and sulfates of calcium and magnesium, that water is permanently hard water. It is difficult to remove the permanent hardness, to remove the calcium chloride, remove calcium sulfate, magnesium chloride and magnesium sulfate. It is easy to remove the calcium bicarbonate and magnesium bicarbonates. So first we have methods of removal of temporary hardness. How temporary hardness can be removed? There are two methods to remove temporary hardness of water. First one, boiling. We just have to boil the water. When we boil the water, what happens to calcium bicarbonate I am taking? On heating, this is in the water. On heating, this calcium bicarbonate changes to calcium carbonate, which is not soluble in water, it is insoluble. So it will settle down in the form of precipitates plus water and carbon dioxide. This will evolve out and this will settle down, and then we can remove it by filtration. There is no bicarbonate left. It has changed to the carbonate, which is insoluble and settles down as precipitates, which can be removed by filtration. So just by boiling we can remove this temporary hardness of water. Second method is Clark's method. In this method, to the water which is temporary hard, which has calcium bicarbonate or magnesium bicarbonate in it, we add lime, that is calcium hydroxide is added. On adding calcium hydroxide, this formation of calcium carbonate, again which is insoluble, and plus water formation is there. So the bicarbonate has completely changed to the carbonate, which settles down as precipitates. So again we filter this water and hence we can remove the temporary hardness of water. So these are the two methods to remove temporary hardness of water: boiling and Clark's method. In boiling, just heat the water which has temporary hardness, and in Clark's method we add lime into the temporary hard water. In both the cases, insoluble precipitates will form, which can be removed by doing the filtration. After methods of removal of temporary hardness of water, our next topic is methods of removal of permanent hardness. How permanent hardness can be removed, how we can remove the chlorides and sulfates of calcium and magnesium from the water. The first method here is treatment with washing soda, that is sodium carbonate, to this permanently hard water which has calcium chloride, magnesium sulfate. These examples we can take. I am taking calcium chloride and magnesium sulfate here. So to this permanently hard water, when we add washing soda, it will react with these salts which are causing the permanent hardness in water and changes these to calcium carbonate and sodium chloride. Similarly here, magnesium carbonate will form and sodium sulfate will form. Calcium carbonate is always insoluble as precipitates in this water. Magnesium carbonate is also insoluble, plus sodium sulfate. So these will settle down and then we do the filtration to remove these salts from the water. So this is the first method to remove permanent hardness of water, that is treat the water with the washing soda and all these salts which are causing the hardness have changed to insoluble form which can be removed by filtration. Second method, ion exchange method. Ions will exchange here. The ions which are causing hardness will get exchanged. This method is also called zeolite or permuted method. Permuted method. Now what is zeolite or permuted? These are sodium alumino silicates, and in journal we can write the formula Na2Z to represent a zeolite or permuted. So how this is used? For this method we take a big tank. At the bottom we will add the water here, permanently hard water from the top. From here the permanently hard water is there at the bottom part of this big tank. Then on the top of this we are packing small stone pieces, that is gravel is packed here. Gravel. Above the gravel there is a coarse sand, rough sand, coarse sand is packed here. Above sand we have to pack this zeolite, or it's a permuted which is packed here. Zeolite is packed here. And from the top, hard water we have to add into this tank. That hard water goes down here at the bottom part. Slowly and slowly that water will start rising in this tank, and through these layers it will reach to this zeolite layer. So when it will reach to this zeolite layer, what will happen here at the zeolite part? Zeolite is represented in journal, I told you, as Na2Z. It is represented as Na2Z. This zeolite reacts with the calcium salts and with the magnesium salts which are there in the water. And ions get exchanged here. From the name itself it's clear, it's ion exchange method. Sodium will come here and calcium comes here, magnesium comes here. So when calcium comes here, this formula will become CaZ and Na will come out. This will go into the water while calcium will remain with the zeolite. Similarly here, magnesium will combine with zeolite while Na will go into the water. So this reaction will take place here at the zeolite. So zeolite has changed to CaZ and MgZ, while sodium ions will come in the water. So then after moving from the zeolite layer, the water that will come here will not have any calcium and magnesium because they are left in the zeolite. The ion exchange has taken place here. Calcium and magnesium of water will remain here, and from zeolite Na will come in the water, and this water from here is taken out. That is the soft water supply we have here. Soft water is removed from here, and whatever waste is here, that waste water will come out from this. Whatever is left here, waste water. So this is how zeolite will help in exchanging the ions. The ions which are causing hardness in the water will remain in the zeolite, and the water free from calcium and magnesium ions, that water is a soft water. But now if we keep on using this thing, after some time what will happen? Whole of the sodium from the zeolite has gone into the water, and in the zeolite just calcium and magnesium are left. So we cannot use it for a long time. After some time we have to regenerate this polluted. We have to regenerate the zeolite. So how we'll do its regeneration? Next part is regeneration of permuted. To get the permuted back from the top of the tank here, we have to spray from the top. We have to spray NaCl. So when NaCl will get sprayed here, this Na again will come in the zeolite, and from zeolite calcium and magnesium will come back. They will come out from the zeolite. So in regeneration, now this is a exhausted polluted which has got exchanged with the calcium and magnesium of the hard water. When we are spraying NaCl from top, again there is exchange of ions. Na will come here. This becomes Na2Z and CaCl2. So this is again in the Z. Again in permuted the Na has come. So this is regenerated permuted. It can be however regenerated by passing 10% solution of NaCl through it. So again we can use it. Again we can add the hard water into the tank, and we can use it further for removing the calcium and magnesium ions. This method is called ion exchange method. Now next method here is synthetic. This is the third method. First method is using the washing soda, second is ion exchange, and third method to remove the permanent hardness of water is synthetic resin method. Nowadays, hard water is softened by using synthetic exchangers. This method is more efficient than zeolite process. We take two kind of resins here. One is cation exchange resin, another one is anion exchange resin. Two tanks are taken here. First tank, second tank here. Two tanks are here. In the first tank here at the bottom part there is packing of the gravel. The stones are packed here. Even in the second tank at the bottom we have the packing of the gravel. Then on the top of this, on the top of the gravel packing here, we are packing a resin. And resins, like I said, are of two types. This is cation resin, H plus resin is packed here. And this side is OH minus resin. A9 resin is here, and here we have a cation resin. Resins are actually organic molecules. These are organic molecules with sulfonic group here, and in this case we have the ammonium group present here. So they have a big formula. In journal we are writing a word resin for this big organic part. In this resin we have H plus, in this resin we have OH minus. The ions which are required to understand this process, that we have written separately, and for rest of the compound we have written a word resin for this. Now since here cations they get exchanged from the hard water, and here the anions they get exchanged from the hard water, that is why this is OH minus resin, this is H plus resin, cationic exchange resin, this is anion exchange resin. Now how this will function? H plus resin, when we add water here, from the top the hard water goes inside in the first tank. Hard water comes here, passes through this H plus resin. When it passes through the H plus resin, see the reaction that takes place here. H plus resin. And in hard water, we have calcium and magnesium cations. So when hard water is passing through this resin layer, it will exchange the calcium and the magnesium of hard water with this H plus. Calcium comes here and H plus comes out from a resin, and this becomes, to balance the charges, we are writing it like this. So this one will be now your resin. Resin will have now calcium and magnesium ions left here, while H plus will come in the water. So the water that will come here, no calcium and magnesium ions are here because they are left here in the resin. And from the resin, H plus has come in this water. So this water will have no cations except for H plus. Rest all cations of the hard water will be left here in the resin. And this water, when comes into this OH minus resin, the reaction is OH minus resin will now exchange all anions. I am taking example of chloride anion. This will come here. So this becomes Cl minus resin, and OH minus will come into the water. They are in water. This one will be in water. So when the water, which will have no cations except for H plus, will come here, has anions, all anions will get exchanged with OH minus. So anions are also left here only as the Cl minus resin or other anions, and from this OH minus will go into water. That means the water which is coming here will have only H plus cation and only OH minus anions left in it. This water which will have only H plus and OH minus ions present in it is called deionized water. Will not have any cation or anion except for H plus and OH minus. So free from all soluble mineral salts, whether it is calcium, magnesium, sodium, any kind of salt, there will not be any soluble salt left in this water. So this is a pure demineralized water. It's a pure demineralized water. So these are the three methods to remove the permanent hardness in water. First method is the washing soda method, second method is ion exchange method, and third method is synthetic resin method. So there are three methods to remove permanent hardness of water. So this is for today.